Okay, very good. So let's go to the second part of the lecture about simulation-based inference. Thank you very much for joining this part. So today, what we want to do is to explore a bit the topics that we have not yet covered about simulation-based inference. And for this, let me go to the slides and the outline for today. So before we start with the topics that will be new for today, I'll give a very brief recap of what we did last week, just to remind you about the overall framework. And then we'll discuss in more detail something that I announced already last week, and this is the notion of an autoregressive model and how this is connected to normalizing flows, something that you use for simulation-based inference. Then the next section is about sequential methods of doing simulation-based inference, which is a particular implementation that is supposed to increase a bit the precision of your posteriors. And then I'll talk about diagnostics of your posterior results, good practices, and a practical workflow for simulation-based inference, while then hopefully being able to close with a few examples how this is employed in practice, and that well highlights a few of the different mechanisms and paradigms we have well had a look at so far. All right. Of course, you can always ask questions as last week. So just ping me when there is something you would like to have discussed or clarification about. As I said, let's quickly recap what we learned so far last week about simulation-based inference. And this has to do with, well, the typical problem in science, the inverse problem. Once I have data and I would like to know whether my observation that I made is actually supporting or not the model that I used as my preconception about how this particular observation or mechanism in nature has, well, evolved or has been conducted. And solving the inverse problem is in simulation-based inference done in the Bayesian way. So we use Bayes' theorem in order to get posteriors for our parameters that go into a model that is supposed to describe reality. And we can test this given any observed data x0 is here. This again makes use of the different quantities that go into Bayes' theorem. It's shown here in this formula. So on the left, you have the posterior. What are the values of my parameters given, conditioned on a certain observation? Then here on the denominator and the numerator of your fraction, you have the likelihood. That is, given the parameters of my model, what is the likelihood of seeing a certain observation or sample of reality given the model? Then this quantity here is the so-called prior. So what is my prior belief in a value of a certain parameter of the model? And the denominator here is called the evidence term, and the evidence is a quantification of what is the plausibility or probability of observing a certain data sample given the overall model. Right. And in this setting, we can sample from a joint distribution of parameters and data to gain, well, realistic or stochastic observations that we think our model would produce and would correspond to reality, which is typically called the forward simulator. And we use this in simulation-based inference in the circumstance where there is no likelihood function available, or this is too hard to evaluate for our numerical purposes. And we discussed several methods that can be employed. If you have a likelihood, what you can do is a typical Bayesian approach of using a Monte Carlo Markov chain or a nested sampling in order to get a posterior, which doesn't need any simulation, but only the likelihood function, as well as Hamilton Monte Carlo methods or variational inference, where you also need a likelihood function, but also gradients. So you need to be able to compute gradients of your likelihood function as a score. While simulation-based inference is in contrast to these more traditional methods because SBI does not rely on the likelihood function, but rather on simulations only. So your joint draws of parameters and samples from an underlying simulator or model of reality or the particular process you're trying to analyze. What we've also seen is that there are different notions of how you can perform simulation-based inference, in particular three flavors called neural posterior estimation, neural likelihood estimation, and neural ratio estimation. They are different in what you learn. For neural posterior estimation, you would learn directly the posterior distribution of your parameters given an observation. And therefore, you use, some proposal distribution or some distribution that is flexible enough to adapt to the correct shape of the posterior you would expect. Then you can use the same kind of proposal distribution to be modeled in neural likelihood estimation, where your target is, however, the likelihood function, which in principle possesses the same kind of properties, so you can use the same prescription there. While neural ratio estimation is rather targeting the posterior to prior ratio or the likelihood to evidence ratio. So you don't directly infer a posterior, but a related quantity that you then need to transform into a posterior. We have seen that you use different loss functions to do so, typically a negative log probability loss for neural posterior and neural likelihood estimation, while neural ratio estimation can be recast into a binary classification problem so that there you would train on a binary cross entropy between two classes of a different, instances or different classes of simulations. Then the network you would use for this, and this is where the neural part comes into play, that all these methods are best performed with neural networks in the background to make them feasible, is for NPE and NLE, a normalizing flow. We'll discuss this in a minute in more detail. While for neural ratio estimation, it is very simple in terms of networks, since it's a classification task, so you can just use a feed-forward multi-layer perceptron network or something more fancier, a recurrent or residual network. Now, in terms of posteriors, what you gain is for neural posterior estimation, of course, directly a posterior that you can evaluate. While for neural likelihood and neural ratio estimation, you would need something like a Monte Carlo Markov chain to sample posterior samples from it, or some reweighting scheme, depending on what you're doing. In all of these cases, what you get is something called amortized posteriors, and they have the advantage over the typical traditional methods that they work for any particular observational data you might show to your derived posterior, while traditional methods that use Monte Carlo chains or nested sampling, Hamilton Monte Carlo, or variational inference all are only valid with respect to one particular target observation, while you are not able to change your target to a different one and still get an inference. You have to repeat the whole chain. Also, for these methods, it is important to note that you perform trivially marginal inference, so you can just marginalize over nuisance parameters and parameters of your model you're not really interested in terms of having an inference for them, while this is harder for traditional methods. And also, you don't really have to include any compression in terms of summary statistic that gives you a kind of a downsampling in dimensionality of your training data that the simulator produces, because you can use networks that do the compression for you on the fly and just put them in a chain in the whole framework. So that you first do an embedding network and then use the network that actually describes the derivation of your posterior likelihood or the ratio. So this kind of replaces handcrafted summary statistics. Right, and this is what we discussed last week. And today we want to go a bit further and discuss some more features and aspects of this particular scheme of Bayesian inference. And to start with, I would like to at least highlight a bit more the nature of normalizing flows and how they are related to autoregressive models. Because also what we discussed in the very beginning of last lecture was this very universal property of any probability density. If you have a joint probability density, and if you remember, you can decompose this into a product over many conditional probabilities in the following sense, that your joint probability for any random variable x1 to xd is the product over many conditional probabilities, where you iteratively condition your following variable on the ones that came before that one, as reads here. So you start with your, so to speak, prior of x1 times the conditional probability of x2 given x1 times the probability of x3 given x2 and x1, and so on and so forth until you reach your whole dimensionality of the problem. Since this decomposition is universal and this is an identity that holds true, you can use this to your advantage in these so-called autoregressive models. And what you do is, in principle, if you want to train a posterior density of many parameters, then you can parameterize each of these conditional probabilities themselves and kind of use this conditional fact in a sense that, well, your condition here is that parameter xi depends on its past, and past is basically all the previous variables, so from 1 to I minus 1. And this whole conditional probability can be parameterized in any way you want. It can even become a neural network. And this is what is being exploited in most of the cases, especially in normalizing flows. Okay, so let me give you some examples of this, how this autoregressive principle in general comes into play. So you have, for example, in time series, that your observation or the variable you would typically record or observe are observations at different times. And you can model this, or this is used also in machine learning contexts in different models or architectures, like recurrent neural networks are a particular example for this, how this is used. And in image generation, you could have, for example, pixels in your image that are a certain order. And basically, what you say is that a certain pixel is influenced only by its past, so by a certain part in your image. This you can write down as this kind of chain of conditional probabilities. And this is implemented, for example, with pixel recurrent neural networks or with pixel convolutional neural networks. This is a variation of this. You could also have, like in the domain of audio synthesis, some waveforms that play a role in this analysis, and wave nets have been implemented to, well, mimic this feature. And there is something more recent, like large language models. There the variables would be tokens, and there will be a particular lecture also on large language models, and we'll explain what tokens are, but tokens in principle are something like words or a group of words, even a sentence. And these work in a sense that they are all conditioned on tokens that came before the next token. So kind of the prediction of your large language model is the next word depends on its past, so the tokens that have been put there before. And large language models are a way to implement this, like GPT, Llama models. All of these kind of use this autoregressive scheme to predict what is the next token in your series of tokens. Yeah, and you can also use this for density estimation, as I said, where your components would be the parameters of your model, and we'll see or go into more detail what the different types for this particular normalizing flow scheme are. Right. So, as I said, just to make this more diagrammatic, or at least to have a little picture of how this works for those large language models. If a token is just a word, doesn't have to be, can be more than a word, you have exactly this decomposition of your sentence that each word is now depending on its past or being conditioned on its previous words in this chain, so that the prediction of your next word will depend on what already has been said in the sentence. And the same you can do also for pixels in an image or in a time series of observations and so on and so forth. So this underlying principle is kind of universal and can be applied to many fields, not only normalizing flows, what we will discuss in the following. So for this type of transformation, there are different ways how you can implement them. So let's start with something called the autoregressive model in its simplest form. That is starting with Gaussian conditionals. So you can, for example, imagine that you now want some kind of joint posterior parameters, and all of the conditional probabilities are modeled as a Gaussian. What you can do is you can parameterize what is the mean of this normal and what is its shift. And sorry, shift and mean is the same. Basically, the mean and the standard deviation, which is here parameterized with these two parameters, mu and e to the power of alpha I. So basically, each of these conditional probabilities gets its own mean and its own standard deviation, which comes from parameters. And these parameters are then, in return, parameterize themselves as a certain function. And this function here then acts on exactly these parameters from, well, 1 to I minus 1 for mu and alpha. So this is taken from exactly this early paper that implements this autoregressive model for these transformations or normalizing flows. And the idea is then to proceed in this sequential way. So you get these conditional posteriors in order, not posteriors, but just probability densities in that way. But the transformation is very simple. So you just start from the first one, which is just standard noise. So you draw from a standard normal with mean at 0 and standard deviation of 1 as your first random variable. And this you then transform into the next variables, which are the parameters of your problem, via this transformation of shifting your initial variable by mu and scaling it by this e to the power of alpha, which is then producing exactly what I said, having conditionals in terms of normal distributions with shifted parameters or scaled parameters. Right. And doing so would produce you then, if you go back to the notion of what a normalizing flow should do, a transformation law. And to write down the transformation law, what we needed is the Jacobian of this particular transformation, how you move from your first initial random variable to the last one. And this requires here taken the derivative with respect to the u variable. And as this is just an affine transformation, so affine transformation is a fancy way of saying it's a linear function, would produce a very simple derivative. So you get basically only the scaling e to the power of alpha I. But because you're only applying this to your particular parameters that are in the past of the parameter you are currently analyzing or trying to parameterize, you have this lower triangular shape. So, of course, you build a matrix that is built incrementally from being only filled at a diagonal to then this lower triangular shape, because more and more parameters will be in the past of the next parameter in the chain of parameters of your normalizing flow. And this is computationally at least less demanding than having a full transformation that is not only taking into account the past of your parameters, but takes into account all parameters. This is why this is computationally favorable. And of course, you need to make sure that your transformation is invertible and how you design the parameters in order to make it a normalizing flow. Okay. Yeah, of course. As I said, then in order to perform the particular step of having a normalizing flow, you perform the inversion of, well, x to u. So you perform the inverse, express your old variables in terms of the new ones, and you have these derivatives with respect to the parameters that you need to take into account in this formula of normalizing flows, because you have this Jacobian that transforms your volume in your probability space. And you do this in this particular way with this lower triangular matrix, which is numerically at least easier to digest than a full dense matrix. And you can write this down and compute this more or less easily, which is then called MAF as a scheme for performing these normalizing flows. Why is it an MAF? Well, because it's based on affine transformations. So it is intrinsically a linear transformation that you use, but the idea is if you have many of these affine transformations, you can eventually reach something that is nonlinear if you have many of those layers and transformations composed with each other. Right. Well, now this is a bit tedious to do if you have to compute this well for all of these functions. So what you would rather like to do is to compute all of these different transformations in one go and not one by one. So in practice, what you would implement is this MADE algorithm, so the masked autoencoder for distribution estimation, which is just a simple feed-forward network that does a masked weight matrix scheme in order to compute all of these mu and alpha parameters at once. So you kind of have this neural network feed-forward architecture, if you want to envision this. And in order to have this implementation of only computing the parameters for the past of a certain variable, you just mask the output one by one for each of the output nodes, so that it can only gain information from nodes that would encode something about the past and not all of the nodes. And in this way, you can just compute this full chain of parameters in one go without having to do it in a for loop or whatever. So this is just making it parallelizable on GPUs as a scheme. Not so important, it's very technical, but just that you've heard about it. Yes, and what you would do, as I said, is to stack many of these mates into a flow-like architecture so that then eventually they become very expressive because you have many of those layers that do these affine transformations. And in the end, you have an expressive normalizing flow that can go from a simple standard normal distribution to a complex posterior like you need for your problem. Yes, in principle, as it's stated here, each layer can in principle have a different variable ordering, and this will also break the symmetry and increases the expressiveness of your normalizing flow. Right, and with all of this made structure, you can have a very simple density evaluation and sampling, so to make this accessible on GPUs and parallelizable. This is basically the idea here. So this is one version of doing normalizing flows, these masked autoregressive flows. Then you can also perform basically the inverse of that if you want to do this variational inference game. This is just to mention it and as a summary here on the slide. But what you typically use in simulation-based inference is the forward parse where you have these MAF, these masked autoregressive flows. And you use this in particular for newel posterior estimation or to a small extent newel likelihood estimation because, well, it is just something that works, but I want to mention here at least that in order to make this work and to make it expressive, you need a lot of these layers. What you could do instead is yeah, do you need this coupling layer? Let's skip over this, it's too technical. Is the fact that we are forced here to an affine map. So intrinsically, this is, as I said, very linear. It stays invertible, differentiable, monotonic, as linear transformations are. But the only thing you can do is scaling and shifting all of this. So what you like to do is, of course, to express posteriors that are very nonlinear. And you will need nonlinear transformations. So getting this done needs a lot of layers, as I said. And individually, each layer itself is limited in expressivity. So what you would rather like to do is something more expressive per layer that eventually will also reduce the number of layers you need in order to reach the expressiveness you need for the problem, which also reduces the computational overhead of your problem. And what people thought about there are something I already mentioned last time, these monotonic rational quadratic splines. And to recall what I talked about last lecture is the idea of a spline. So you use these splines in a certain interval of your parameter space. And in each of these intervals, you would create a certain number of knots. And these knots would be connected by a certain spline that is of this particular form. So it's a rational spline. And it can become quite expressive because it is nonlinear and quadratic. The only thing you need to make sure is that the overall spline within the interval you've chosen stays monotonic. And you need to make sure that at each of these knots you have all consistency conditions being fulfilled, so it is continuous and differentiable. Of course, as you see here, differentiable is necessary, but it doesn't have to be twice differentiable, as you see here in this example. And the implementation is then, because you can, in fact, analytically invert this transformation of splines, make a normalizing flow out of this if you have many layers of these splines. So the idea here is, again, to be autoregressive and to apply these splines in the following sense, that you split your variables that you have at a certain layer into A and B. And then there is one path for A and B. Let's say for part A, you would apply a neural network to these kind of part or subset of your parameters that describe this. And they then are fed as output into this spline transformation. So with these parameters, you would then produce your normalizing flow spline. And basically then the spline takes as input this neural network transformed subset A and as well subset B and applies the spline. So the idea here is that you not only have splines, but also your splines depending on parameters that are transformed by a neural network in order to increase the expressivity of all of this. Right. And this subset B is then everything that is transformed by a neural network and a spline, while the subset A itself is just passed through this layer without doing anything. You just concatenate these two subsets again to form then the final output for your parameter layer ZK. So this is kind of the idea here. And you perform this for each of these steps again in this autoregressive way. So parameter by parameter and path of the parameter then split into this particular way. Basically, what happens is that because of using now splines, you're not forced element-wise to a fine transformation, a linear transformation, but you can be non-linear. You have a lot of output, of course, because you have all those knots, all the derivatives in your model. It's non-linear because you have these rational and quadratic spline functions. And it is invertible and analytic because there is an explicit formula which does the inversion. You can look it up in the paper that I put there as a reference. And there's also a closed form for the derivative of these spline functions that is also given explicitly in this paper. So this can all be done and implemented very easily. And because of the expressivity that you give to this particular framework, it uses much less space on a GPU and many less layers than you would use for these MAF normalizing flows. Just to give you a little intuition, as a little sketch. So if you do these affine things, while your transformation between the input variable and the output variable is really just linear, or splines do it, well, in a fancy nonlinear way. So you can easier reach, let's say, a multimodality of your posterior than you could do with linear transformations. That's, for example, one thing you want. Right. Yeah. Basically, what you do is for simulation-based inference in this landscape of architectures that use the autoregressive principle is either MAF or neural spline flows that then go into your density estimation, while you can, of course, rely on other methods that have been explored in literature, but at least for common applications in simulation-based inference, rather stick to the gold standard that are those neural spline flows, or in special cases, these masked autoregressive flows also work and can be useful in some cases. While, just to say it again, this chain rule on the autoregressive nature is also present in large language models and variational inference. So it is a topic that is also interesting apart from simulation-based inference. Right. So just as a summary, as I just said, the autoregressive principle is based on a general property of all probability densities. It can be used for simulation-based inference and density estimation, but is also present in, well, time series, image generation, or language models. What we would rather use here are our autoregressive models for normalizing flows, and you can implement them if you have it in an autoregressive way in an easy to compute Jacobian matrix, which typically has a triangular shape, which reduces the computation needed to derive your final answer. There are several ways you can implement then normalizing flows as these masked autoregressive flows with affine transformations being basically the operation you need to invert and to differentiate. or neural spline flows, which are these rational, quadratic, or even cubic transformations that are intrinsically nonlinear, but that have more expressivity and are currently the gold standard for performing normalizing flow architectures, especially neural posterior neural likelihood estimation. Right. Before I go over to the next topic, questions about this more technical part about normalizing flows and the autoregressive nature of these models. If not, then let me introduce the next topic, which is, well, basically just continuing the general flow of how you would do simulation-based inference. So what we've seen is that the general scheme for simulation-based inference is either done in these three flavors: posterior, likelihood, or ratio estimation, or if you want to be kind of mundane and stick to the roots, you can also do this approximate Bayesian computation, which is the predecessor of all these newer ways of doing it. But they are kind of limited to in the following sense, that they are single round inference tasks and simulation and training steps. Well, this has the advantage, of course, that it gives you this amortized posterior that you can evaluate for many target observations. However, they are not specific to one particular target observation. While these traditional methods, Markov chain Monte Carlo, nested sampling, variational inference, all are specific to your observation. You can also do this in simulation-based inference and be specific about one particular target observation and then reach even a higher precision. And to do this, you need to perform sequential simulation-based inference that then adaptively addresses the fact that you want to zoom into the posterior space for one particular target observation, which kind of breaks this feature of being amortized, but you gain a precise posterior if you wish. Well, why would you do this, or what would be the general approach to do this? Well, if you have one specific target observation, you can, of course, draw from a prior, and you start with your general prior as you would do in simulation-based inference, do the whole chain, and get a posterior in the first run. This is just the same as we did before. But now that you have a posterior, you can ask the question, okay, can I use this posterior as a proposal distribution for a prior of a next round of simulation and training in order to get an update on my posterior based on this proposal distribution? And this is exactly what you do in a sequential simulation-based inference way. You do it in the first round. You use your posterior in some way as the prior for the next rounds to start again the simulation process, the training process, and the inference process with the exact same target observation. And there are two main strategies that you use, and it also depends a bit on what flavor of simulation-based inference you use. You could either do a prior truncation, depending on the output of your posterior, or you do it a proposal based, and this is using the posterior itself as a prior for the next round. And we'll come to this, how you do it. So prior truncation is the simpler approach to it, because what you do is you just iteratively discard the low density region that you obtained in the previous round in terms of your posterior. So let's say you obtained a certain posterior in your first round for each of the parameters you're looking at, and then you can zoom into this posterior range where a certain mass of your inferred parameter should sit. And you can simply forget in the next round to simulate parameters that are in regions of your posterior that are covered by the prior, but where the posterior just doesn't live. So this is kind of a useless part of your original prior space that the target observation will never populate. So why should you simulate this in the next run? And this is just basically expressed by this formula here. So you would retain only those spaces in your original prior range where your posterior predicts a certain probability above a certain threshold. And the threshold should be defined by you. What should be the threshold? Well, depends a bit on the output of your posterior, but you could say if the posterior is something like a Gaussian, then a 5 sigma cut is safe. If it is not exactly Gaussian, then you can go to something like a highest probability region. So you can really read out what is the probability in this posterior, what are its values, and then just cumulatively integrate this posterior and see where most of the mass for the integration comes from and cut away all the outer regions that are just not contributing much to the integral. Right. You can do this either in, and let's have a look here, in a simple way or in a more fancy way. So the simplest way to do this is a box truncation, where basically for each parameter, so each one-dimensional marginal posterior, you look into this posterior, you truncate it as a box, you throw away all the region that is completely negligible below the threshold for your observed target, and then you just stack all of these posteriors together to form a joint posterior, which then will look like a box. Or you could be more fancy and do this highest probability density or mass screening that actually will also then retain the correlation structure of your posterior and parameters. So, however, this requires the density evaluation, so it's numerically a bit, well, more involved to do, but it doesn't just, well, ignore the fact that there are correlations in your parameters and keeps the correlations, but it requires more evaluations of the posterior. So there's a bit of more numerical overhead. Of course, it is advantageous to do so because otherwise, as you see here, if you do this box truncation, you still have parts of your prior range that are completely useless to simulate because your target observation just doesn't live in that space. So you can either sacrifice a bit of computation time in evaluating your posterior or sacrifice computation time in simulating useless samples that are not informative anyway. But so that's this strategy. A different strategy is, however, using proposal distributions. So there, the idea is to actually use the posterior as the proposal for your prior in the next simulation round. Yeah, it's the same iterative scheme. So in each round, you get a posterior, which is then used as the proposal prior for the next one, for which to draw parameter samples to simulate training samples for your simulator, for your neural network. And you have, however, to correct if you do this particular scheme. Because if you don't correct for it, you will bias your problem. Since you started from a large prior and you zoom into the space while then sequentially shrinking your prior range, which messes with the initial probability density that was assumed for the problem to be there. So you kind of have to correct for the fact that you are throwing out volume of your initial space. And you can do this correction in multiple ways, as is shown here. In particular, if you have as your proposal this posterior of your previous round, then you would correct by the overall prior to new prior ratio and kind of re-weight different spaces in your parameter range so that it is correctly accounted for. However, if you just do it in this post hoc way, so you just do your run, and after this, you just feature this into your new sampling algorithm, you have to assume that your posterior is kind of Gaussian, and then you do a Gaussian mixture model in order to actually be able to draw parameter samples. Since you need to make this assumption that this is all Gaussian, more or less, you might struggle with the fact that reality might be different and your posteriors are multimodal, have heavy tails that are non-Gaussian, which then leads in return to something called mode collapse or other kind of unwanted features that are not the best posterior you could have if you weren't making the assumption of Gaussianity. Right, but this is this necessary evil you need to do if you want to have this post correction of your prior. This is called sequential neo-posterior estimation A as variant A of during the sequential inference. And in particular, this is possible also in principle only for neural posterior estimation, what I'm saying here. Then, of course, if there's variation A, you can also have variation B. Variation B is more fancy in a sense that, okay, you need to do this reweighting of your prior space, but you can do this during training. So here, what you do is you modify the loss that you're training by introducing some importance weights. And the importance weights are kind of just the same weights as before. So you have your initial prior and your new proposal prior, that is the posterior of your previous round. But these are now part of the loss function that you train on, plus, of course, the new posterior for this particular round of the sequential map training round. Yeah. Right. You can do this. This doesn't require you at all to specify what is the distribution you're assuming for your priors. They don't have to be Gaussian, they can be whatever. However, what can happen is that this becomes unstable because these importance weights that you have here, they have very different orders of magnitude in some cases. So numerically, this is not a stable, most stable thing you can do. So yeah, it is dangerous sometimes. What you can do, of course, here is use normalizing flows. So they work very well with this method. And if there's A and B, then there's also a variation C of this, which is the gold standard that people use currently in the literature. That is kind of trying to combine A and B, which is so-called APT or automatic posterior transformation, which is based on atomic proposals. So this is very technical. And what you should retain here in principle is that this tries to do both. So it tries to use some kind of a hyper proposal distribution that is easy to evaluate, but to also introduce then these or importance weights during the training as a part of the loss function. So that this hyper proposal distribution is easy to evaluate and produces these importance weights that are not scattered across orders of magnitude. How this is done in a technical way, it's not so important, but you should retain here that it does both versions in a way that is numerically stable and that you can easily sample. Okay, And this is basically how you do it for nil posterior estimation. So, what is the general flow then you should do for sequential inference? Well, you should first think about what type or flavor of simulation-based inference I want to do. And depending on this, you have multiple options. Well, for a nil posterior estimation, what you would likely do is to do this chain of proposal distributions. And in particular, this sequential posterior estimation C, where you have best of both worlds that is numerically stable and that works. Prior truncation can be done too, but this is typically not the best you can do for posterior estimation at least. If you have sequential runs for new likelihood estimation and new ratio estimation, then prior truncation is straightforward. And that's probably the best thing you can do there because it's easy to implement. While proposal-based methods do exist, but this requires more care. Especially in neural ratio estimation, this becomes hard. Yes. A caveat here is also then about the marginalization, as I say. Since you are now zooming into the space for a particular target observation, you typically lose marginalization properties. They might still be retained in the, well, surroundings of observations that look like your actual target observation. So there is a certain notion of amortization still there, but it is very less so than if you just would train for one round. Also, combining marginalization and sequential neural posterior estimation typically leads into trouble and it doesn't work at all. The others might do, however. And just to mention it, there is also a very recent way of doing simulation-based inference in a dynamic way. So what the people there are doing is to do sequential inference, but not in rounds, but doing it round-free, asynchronous and parallelizable. So what is the idea behind this? Well, you just need a certain initial set of training samples and you start your simulation-based inference training. After a certain number of training your network, you would evaluate this, get a posterior, then use this posterior as your new prior, use or simulate more samples that then update your store of samples, and then kind of in an asynchronous way continue training with more samples than before and doing this kind of in this stream and flow forward. So it is a bit fancy. It avoids all of this sequential stuff, but you still need to do this reweighing of your prior and doing it in the loss. So you still need to do it, but it has advantages here and there. Okay, right. This is about sequential inference. Are there any questions so far before we come to another aspect of the chain? Right. Right. If not, then let me tell you about now probably the most important subject in this lecture, and this is about calibration and validation of your posteriors. So for now, what we've done is we just explored how you technically do this, but then I never said, well, okay, you get a posterior and what the hell's going on with the posterior? Should I take this for granted that this works, or do I just get bullshit that has nothing to do with reality and this method doesn't work at all? Well, that's why you should do diagnostics and look at the output of what you're producing. Because neural networks can spectacularly fail in many different modes, and you should just verify that your output is what you want. In Monte Carlo Markov chains, you are evaluating a likelihood function. This is a very well ideal statistical case that you can easily evaluate, and you know when you do it, you get an answer based on a likelihood function it's a valid posterior. If you do simulation-based inference, this statement is absolutely not true, and you just might get rubbish. So you should check the convergence of your algorithm. And there are some built-in ways you can use. Now, undertrained networks, poor architectures, insufficient simulations can all lead to posteriors that look reasonable, but are completely off. If you look, for example, in this plot here, in green, no, in gray, you have the technical ground truth of how your posterior should look like if you run a Monte Carlo chain, let's say, and you get the unbiased truth of how your problem is solved. Now, what you could produce is like something like the blue curve that is too wide. In a sense, that's not a problem. It just means that the posterior you've just got from your algorithm is overly well conservative. You could be much better, and you just didn't solve optimally your problem. You could also have something that is like the dashed green curve, that is too narrow. In this case, you're overconfident and you just say that I can constrain my parameters with an observation like this, which, even given an actual likelihood, is not possible. So you're just claiming nonsense. Or, as shown here in the red curve, your result could be biased. So you might have the correct shape and even width of your posterior, but you're biased. So you infer something that is not right. And all of this can be checked with different diagnostic methods. And we'll cover these in what follows. Now, these are so-called posterior predictive checks, and they're all based on basically using the estimated posterior, simulate data, and compare it to observed data if you have access to it. There might be situations where, of course, you have simulated data and you can produce many different observed data sets, like in tabletop experiments that you can repeat. But then you can be in the more, well, unfortunate situations where you only have one observed data set, like if you do astrophysical or cosmological observations. That's a bit limited, and there it gets a bit harder to do diagnostics, but you can still do it. Okay, and what you want is basically that simulated data and observed data should kind of coincide if your posterior captures the correct data generating process. What I would like to say here right from the start is that even if your posterior is passing all of these predictive checks, it doesn't sufficiently guarantee that what you get is optimal. You might still spectacularly fail, and we'll discuss instances where this happens. However, as a first sanity check, what you should always do is to use the posterior you get after you inferred something for a target observation and to draw observations from exactly this posterior and to look at the observed data sets if they are anything like the actual target observation you have used. If that's the case, at least you're in a good space and you can go on with the next sanity checks. So, what can you do? Some lightweight stress tests. Well, you can remove parts of the observed data and just check if your posterior changes sensibly in any way. So if I just change my data a bit, put a mask in here and just say, okay, this information in my target observation is not there anymore. How does my posterior react to this in a reasonable way? Is it still able to capture the nature of the parameters that should go into to produce this? Then you can also start changing the architecture of your embedding network that derives the summary statistic, or to change the layers of the normalizing flows? How many hidden layers do you have there? Is there any sensitivity into undertraining or overfitting the data? What is my validation curve that I get? And if it's all of these, and then you can also actually do training with fixed random seeds. So to not just use computer time as a random seed, but actually use different seeds right from the start and compare what is the output of my posterior estimation, likely estimation, ratio estimation for different random seeds. If you see high variance and instability, this is already a sign that maybe the architecture is not the best and it's not very stable. But even if it is, doing this on many random seeds is not a bad idea, because intrinsically, having a neural network in the pipeline introduces some epistemic uncertainty. So the random initialization of your neural network weights and biases gives some intrinsic noise and variation to your problem. So if you start from different random seeds, you get different initializations of your neural network, even if it's the same architecture. And you can, in the end, even take an average over different random seeds and quote this as an additional epistemic uncertainty on top of your posterior. So this is something neat that you can do. Right. And if you've done that, you're good to go to the next diagnostic checks. Right. What could these diagnostic checks be? Well, they are typically called coverage diagnostics, and they are a kind of a ranking principle and telling you whether or not your posterior makes sense or not, which is then the typical gold standard for simulation-based inference tasks. So what you need to do this is basically a set of target observations. So here, this is not based on one single target observations, but L target observations of pairs of parameters and simulations. So here what we are leveraging or exploiting is this amortization feature of simulation-based inference. And for each of these target observations, you can get a posterior. And what you then do is to define a certain ranking metric that is defined by a certain projective function as done here in this example. So for all of these examples, if you have so and so many posterior samples from your derived posterior for your target observations that you have, you can count, okay, if I employ my projection of this parameter sample to the real numbers, how do they compare to my true values? Well, then you take the average or whatever. In this case, you typically take the average over the samples that you've drawn from your posterior. And you, in the end, get these ranking metrics R that should be distributed in a certain sense if they pass the coverage tests. And what type of coverage test they should pass depends on this function f that you employ to your parameters that transform them or project them in a certain way. And depending on this function, you have different checks that are done in the literature. So for example, you have the choice of saying my projection function f is just one parameter of it at a time, meaning that you get a simulation-based calibration that tells me per parameter what is the overall occurrence that this parameter is less than the actual parameter, the true parameter that I have, and I count this. And then I weight this, or I take the average of all the samples I've drawn, and I have in total L target observations. So I have a nice distribution of my ranks R, and they should follow a certain distribution. What you can also do is, instead of just projecting out one parameter, you can take the log probability, so the full log posterior probability, which will then become the expected coverage. Or you can take, for example, the Euclidean distance between your points or parameters to any random reference point in your parameter space, which is called TARP. Right, so let's have a look at this simulation-based calibration first, where you project out one parameter and you just want to know how many times does it occur that this parameter that I've projected out is less than the true value of the parameter it is, averaged over the M samples I've drawn for the L target distributions I have generated. Well, you have these L calibration metrics, and what they should be are exactly uniform from 0 to 1. If they are fulfilling this criterion because this is exactly what you would expect. So it should just be completely uniform and random across 0 to 1 if they are less than your true parameter, in this case. There are certain ways you can identify a deviation from this. If you have a U-shaped metric here or distribution histogram of your calibration metric values, this is a sign of being overconfident. So the edges here are kind of overconfident, and it happens too often that you are much less than your actual prediction or much higher than your true value, then it should be the case. If it's underconfident or overly conservative, a different word for it, it has this inverted U shape, and it's more like, yeah, a mountain, if you wish, meaning that you are just too often in the range where you are below your parameter. And then you can have some weird cases where you have a skewed distribution, which would rather be an indication that there's a certain bias. So you rather go to a different value than the true value is, and you cover this more in that region where your bias would put you than in the actual region where the true parameter lies. Of course, the strength is that you can do this for all parameters, and you can identify calibration issues for all the different parameters, but it doesn't really detect correlation problems among these different sample sets. Then the other option of choosing a function is the projection with the log of your posterior or probability density for the parameters, which would then produce you a coverage plot. So this rather goes into the direction that we discussed also, well, last lecture, of just saying, what does it mean for a Bayesian posterior to be a Bayesian posterior? So what you would expect for a Bayesian posterior is that if I would repeat my observation many, many times, then the prediction of all of these posteriors should be such that the true value is averaged over all of these observations, like 68% of the time in the 1 sigma interval of my posterior, 95% of the time in the 2 sigma interval of this posterior, averaged over all of these observations. And this is exactly what you would check with this coverage test. So it gives you an empirical measure of how well your posteriors behave as a Bayesian posterior if you would repeat this experiment many, many times. So let's have a look at especially this diagrammatic or plot of what you would expect. You see here on the x-axis the nominal coverage. So this is basically saying that nominally in my 1, 2, and 3 sigma interval of the optimal posterior, I should have this and that coverage of the true parameter or the parameter that I infer in my run. You can compare this in this empirical coverage way if you evaluate exactly this metric above across many of these drawn target observations. These posteriors should behave in exactly the same way at best, shown by the black curve. So they should just lie on this diagonal line. My empirically found posteriors should also, in all of these cases, have their 1 sigma, 2 sigma, 3 sigma intervals in the right places that the recovered parameters land in the correct frequency in these intervals. If this is not the case, if you're conservative, they would be above this diagonal line, meaning that they are actually broader than they need to be. If they're overconfident, they would lie beneath the line, this diagonal line, saying that they are actually more than often wrong and would tell you that my true parameter is not exactly in the correct nominal width of my 1, 2, or 3 sigma interval. The strength here is that this gives you some idea about the joint distribution because you're working exactly with the joint distribution, not just singling out individual parameters. So it can also detect miscalibration in correlations among parameters. However, this is averaged over parameter draws or draws over your observations that you have. So you might end up undercovering different realizations of your observations. So you can't be sure. And especially this becomes obvious if you go to the 2 sigma, 3 sigma regime. There you can end up having not a lot of simulations that would fall into this regime, and it's very hard to give a statistical measure if this is now the correct coverage or not. So you would need a lot of simulations or target observations to do this, which takes a lot of time. And lastly, you have this TARP or test of accuracy with random points, where you basically take a random reference point drawn from your final posterior, and you compute the Euclidean distance to your parameters to this reference point, and you construct credible regions. So basically balls around this reference point, and you measure the distance to this. Basically, and by varying the point, you have a certain notion of how well you cover the parameter space and your posteriors. This is kind of something that is not done too often, but it is a possibility to do in the end. What you typically do is this coverage test with the log probability density and the simulation-based calibrations. So those ratios for individual parameters, which give you a simple way of assessing your calibration. However, as I said, depending on what you're doing, this can be numerically kind of expensive. Especially the empirical coverage test can be expensive because you require a lot of simulations in order to test the wider region of your posterior, in order to test 2 sigma, 3 sigma, even 4 sigma ranges properly. Right. So as a summary of these diagnostic tools that you have at hand, what you should do is just testing data consistency. It doesn't detect anything at all. It's just after getting your posterior, you just evaluate this with predictions from posterior, and you make sure that it looks reasonable compared to observed data. And with the variations to network architecture, there are no weird surprises that make this kind of unrealistic. And once you are sure that that works, so these first cheap sanity checks give you something reasonable, you go on to these coverage tests, like singling out single parameters or doing the empirical coverage to know whether or not there is some overly conservative or overconfident posterior, or if there's some bias in your posteriors. Depending on what you do, you can detect also correlations and include the correlations in these coverage tests, but then it depends a bit on what type of simulation-based inference flavor you're using, what is the best way to go forward. However, to stress it, this is only a necessary way to make sure that your posteriors are good posteriors. It's not a sufficient check because you know you can do all of this, you can pass all of these checks, and your posterior is just your prior. Everything is fine here, but it's just rubbish, nonetheless. So it's not guaranteeing you at all that you have an informative posterior. This needs to be verified in a different way. At best, if you can, with a comparison to a likelihood-based method like nested sampling, Hamilton Monte Carlo, where you know the answer, and you can check directly that your result with simulation-based inference gets to the same precision accuracy as your likelihood-based approach. If you don't have that, of course, and this is also the reason why we have simulation-based inference, in some cases you just don't have a likelihood function to evaluate. You have to rely on these diagnostic tools first to make sure that at least the posterior you get is reasonable and it doesn't look like a prior. And then you have to see further. Okay. Right. I think before we go to the next section, which is about model misspecification, I take your questions about diagnostic tools. If there are none for the moment, I would say we take a break of 30 minutes and reconvene at 3 p.m. to finish this lecture about the technical aspects of simulation-based inference and then to have a look at some notebooks, how this is applied on examples. Okay, see you in 30 minutes at 3 p.m. Okay. Hello, everyone. I hope you are back because we have a bit of materials to cover before we go to the notebooks, which is a bit about, well, good practices and the first part about failure modes of simulation-based inference and what we can do against that and how we can test for this in the very same framework of simulation-based inference. And this is about the topic of model misspecification. So this is exactly the part why you have to check for calibration, in particular regarding biases of your inference. But this gives you also a handle on understanding whether or not you can improve your model. So, as it's written here, what is the elephant in the room? Well, that is that no matter what simulator you are conceiving and you are using here for inference, it will only be an approximation of reality. And the quality of your inference with SBI very much hinges on the quality of your simulator and how faithfully it can represent reality. So the question is, what happens when it does not? And this is called model misspecification, meaning that the true data that you take as your observed data is simply not within the distribution that your model can generate. So, in other words, your simulator does not produce realistic data. Well, what could be the example? Well, there are basically many examples for this, but your simulator might just ignore a physical effect, like the inclusion of, as always, magnetic fields and turbulence. You might just have chosen the wrong noise model that actually doesn't work for your particular example, where you assumed Gaussian noise, but in reality, your noise rather has heavy tails. You simplified your problem by giving it a certain geometry. You discretized the problem so that there are some artifacts because of the discretization. Or there are simply just some missing variables in latent space that can hardly be marginalized over, which are also hard to assess from a simulation point of view, that, however, are there in realistic data. So all of these failure modes could happen. And they will potentially happen when you start working with simulation-based inference, and in particular also with anything you do that is likelihood-based. Because typically, in order to write down a likelihood function, you need to simplify the problem as well. So that's the typical research situation anyway. But what can we do about it? Well, in particular for simulation-based inference, this is dangerous because it might prevent the true posterior to be reached once you even add a lot of training data. And you might never reach the correct coverage, and your tests to make sure that the posteriors are sane completely fail because there is this misspecification that your distribution of the simulator cannot really describe. So, of course, it can be overconfident because of the reason that your simulator is simplistic. It makes some assumptions that cut reality down to something that is overly simplistic. You might still get an inference of the parameters because they are kind of relevant for the process you are looking at, but the actual width of your posterior is wrong. Because in reality, there should be other processes, systematic uncertainty that comes into play. There's some theoretical uncertainty, who knows what. On the other side, you could also be biased because of missing components in your simulator that are there in reality, missing nuisance effects that might be present in reality. Your inferred values for the parameters are shifted kind of constantly. and systematically across the full parameter space, and you get simply a wrong prediction for your parameters. The diagnostics won't probably help you at all because they are based on simulated data, and everything in terms of inference can look fine on simulated data. But the actual sufficient test for having a good and calibrated posterior comes from also working on real data. Whether or not the realism can be captured by a simulator that is there in actual data. Well, how would you at all detect this kind of misspecification? Well, you have some potential ways to do that. I mean, you clearly have these posterior predictive checks against real data. And as long as your particular process you're studying even allows for repeated real samples, this makes it kind of easy to test whether your simulator and the posterior parameters that you draw will create realistic data sets. So that's something specific to the domain that you can or cannot do, but it really is dependent on the actual observation. It will be impossible for anything that observes the universe. There's just one universe, and that's what we have. It's also for these predictive checks interesting to have a look at the specific features that you would expect in your real model to appear and whether it can actually be reproduced from your posterior that you obtain. However, this is always a bit subjective and it requires a bit of domain knowledge to actually pin down and know what you're looking for, which in fact and honestly is true for all of what I'm now going to say. But you have at least some more generic handles in the second version, which is something that has been addressed and analyzed in the past year in the literature, which is called distortion-driven hypothesis testing. And what the idea behind this is basically that you can parameterize distortions to your model with some little epsilon modulation. And you just simply say that, okay, my posterior that I obtain, or the likelihood, better to say, of getting any particular observation given parameters, I can say is whatever the likelihood of the problem is, plus epsilon times this modulation factor. That might also depend on the parameters and the actual sample you're going to produce. Well, then you have neural ratio estimation at hand, which is a way to distinguish between different classes. Well, the ratio estimation itself is distinguishing between samples of target data sets and parameter samples, whether or not they come actually from the same joint or if they are marginal. You can also ask the question here whether or not there is misspecification and epsilon equals 0, or if there is a non-zero epsilon in your simulated observation. And then you can turn the simulation-based estimate for a ratio into a goodness of fit residual analysis. And this is basically the idea behind it. So in general, what would happen is that you define a family of distortions to your particular model. This could very well depend on whatever you're trying to do. So this particular paper that I'm referencing here was using gravitational waves. So what they induced were some Fourier modes or wavelets that perturb the typical observation of gravitational waves in different aspects or frequency ranges of that particular model. But you could also imagine having images as your observation, and you can just perturb your image with whatever, adding different features in the image, adding different components in an image that might be there, might not be there, adding some Gaussian noise in there. All of that is possible. And then for each distortion, you would train a classifier, this neural ratio estimation classifier, to distinguish between simulations that are baseline-like, so no distortion at all, or distorted. And then you apply this classifier to the real observation, and it gives you a log ratio of how likely it is that this particular type of distortion is detected in the real observation. And if the model is required to be, well, respecified in order to include this distortion. So it also gives you an actual quantitative handle on what type of distortion your real data seems to require and what your actual model does not include. Right, and then there are some internal self-calibration algorithms that make this a good method, and you can show mathematically that what they are doing, this paper is basically a goodness of fit residual analysis with an actual quote of what the goodness of fit of your simulator regarding the real data is or not. Right, what you can also do is, of course, a model comparison in ratio estimation. So there you do have kind of access to the evidence of your data given the model, which helps you to state something like this model is more likely to be describing the real data than this model with the distortion. So this is a pretty neat test. Right. And in fact, this is kind of the gold standard that is there in the field, a bit requiring domain knowledge to understand what is missing physics that could be there to improve the noise model, which then captures part of this missing physics in terms of some effective noise or increased resolution of your simulation, which is not always feasible, but fixing the simulator is the gold standard. However, it requires domain knowledge, and this is more like done by hand. The other options that you have are, well, robust summary statistics. You can try to learn summary statistics that downweight features where a model and data disagree. This, however, requires some regularized loss that penalizes the statistics where this mismatch happens. So again, this is possible, but requires something that's, again, handcrafted. You could then also try the third way to calibrate with real data. When you have a little set of real observations that you're also simulating and trying to infer from, then you can try to learn a correction to the model via some neural networks and optimal transport, which leads you then to close this gap in your data and to kind of have a domain shift. But this requires you to have an actual sample size of real observations. In some instances, like cosmology, astrophysics, typically impossible. So it's restricted to a certain kind of inference. And yeah, one thing to do is, of course, to just add more noise to the thing. If you just add more noise to your simulator, of course, you can cover potentially any misspecification by just adjusting the noise such that magically now the real data is within your model at the price of widening your posteriors. And if you do this in a non-guided way, of course, your posteriors might become very wide and uninformative in the worst case. Right. So, what is the practical thing you then do in order to perform simulation-based inference, including model misspecification checks? Well, you should look at, well, what is the method I'm using? Then decide whether or not you perform sequential inference or not. Perform the standard diagnostic checks that at least validate you the calibration of your posteriors. And then afterwards, also given some predictive checks, comparing simulated data to real data, looking for the necessity of misspecification checks. You might want to try with these distortion methods if you have in mind a particular, well, case that might differentiate your simulated data from the real data and you can model what this missing piece is. Otherwise, yeah, try if you have at hand real observations and try to guide your simulator towards reproducing them. Otherwise, well, you analyze the posterior nonetheless, and you report that there's misspecification in your simulator, and you try to quantify what is the impact of that. So just be honest about that and quote that there are limitations, you know about them, and the correction should go along those lines in the future. Okay, so in summary, you should always expect that your simulator is wrong, that there's models misspecification in the problem, since it is probably inconceivable that any of us will ever be able to produce a simulator that is 100% correct. Then test your diagnostics, of course, at least to make sure that you have calibrated posteriors. Do predictive checks from your posteriors in order to have a comparison to real data. And if you see a certain mismatch or a bias, then start developing these techniques that go into misspecification. Whether or not you can apply them depends on your particular target. But if nothing works, then be honest and say that, well, we have these posteriors, we know about our limitations and discrepancies with reality. We will improve on this and that way. That's basically the workflow. Okay. Any questions about this part of model misspecification? All right. Then I just want to name a few good practices for simulation-based inference. In particular, when you should actually use this. So, as I said, likelihoods might be intractable and expensive, and then this is potentially the only thing that is left for you to do, because the only thing you need is to simulate, and that is oftentimes something you can still afford to do. If the simulator is complex, it might take a lot of time, so even there, then you are limited. So it is, however, in that situation, at least, where there is a clear case for using simulation-based inference. Also, if you need amortization, then certainly this is the way to go, because this is the only way you obtain amortization and you can have a real-time analysis for many different cases or observations you might have. You might also want to use simulation-based inference if you want to avoid the use of handcrafted summary statistics that embed your data in a low-dimensional space that might be handcrafted and work in a particular situation, because then you can feed it into a likelihood. But if you avoid this and to retain more information from your actual data, you might want to use this technique, because embedding networks that optimize on the fly with the method itself, the embedding and compression might be more powerful. And of course, also, if you're only interested in a few marginal distributions and not into all of the parameters that your model might have, then this is the way to go, because you can reduce a lot of the overhead for computation if you exactly have this in mind. However, this cannot be stated often enough. If you do have a likelihood, even if it's particular, if you have something like Hamilton Monte Carlo at hand, use this. This is the gold standard. It is kind of cheap and it gives you a correct statistical answer. It's well established, you can check it, and it avoids all of the complexities of testing Neural networks, if they fail or not, and it also avoids you explaining to your colleagues why you use neural networks again and why this is better than what they can do with a likelihood. So it depends very much on the case. So in that sense, simulation-based inference is not a replacement in the future for any of these other methods. It's just something that is complementary and must be used in the places where it makes sense. Right. Then regarding what algorithm should you choose? Well, also there you have several criteria that you can have a look at and that will go into your evaluation of what or not to choose technically, as it's given here in this table. If, well, as a rule of thumb, you should start with nil posterior estimation. This one is, in essence, very simple. You have these normalizing flows. This is a well-established technique and architecture. They do exactly what you want. They use data to train a posterior distribution by shaping the parameters of a neural network. It has a fast inference, it's well studied, and it's a good default. Then, however, you might want to change to a different methods depending on whether or not the parameter space you're analyzing is highly dimensional. Then this normalizing flow stuff might be very slow. You have multimodalities in there, which is very hard to do. And it's also impossible to combine multiple independent observations, where the same parameters would underlie those observations, but you need to stack these observations to be described in an ensemble. Their new likelihood estimation is your friend, and it certainly works. When do you use neural ratio estimation? Well, this one gives you an easier network to work with. Um, and sometimes it might be easier to actually constrain the posterior to prior ratio than the full density. The difference is that with null posterior estimation and likelihood estimation, you always reconstruct the full joint posterior. While for neural ratio estimation, you do not by default. You actually select what you're going to reconstruct. In terms of posterior, it can be a one-dimensional marginal of a few parameters. It can be two-dimensional marginal posteriors. It can also be the full joint one. But if you want to save on time and only need a few of those, this is a friend. You can ask to do it for you. Regardless of what you're using, though, you should use the diagnostic tools that I introduced to you. Right. Then, of course, you'll find more tips in the literature on what to do. One particular, well, tip is, well, as I said already before, ensure that the simulator is deterministic and follows a chosen random seed in order to guarantee reproducibility. Choose priors that are broad enough to cover the plausible parameter ranges, but don't be so broad that you waste computation time. Or if there's already a study in the literature that does a similar thing and uses likelihoods, and you have a notion of what the parameter ranges are, use that. And treat the simulator as a black box, because the SBI methods, they do not need gradients through it, and that's true, in fact. In terms of training, well, it's the typical recommendation you always get for training neural networks. Normalize everything to inputs with the zero mean and unit variance, because, well, neural networks just like that. Monitor validation and training losses, use early stopping, and all of these monitoring in order to verify that your training works well. And in particular for neural posterior estimation, use the spline flows because they are the best architecture currently on the market with the most expressive layers. In terms of validation, well, use that. So run these SPC checks on the per parameter metric, as well as the calibration, the empirical calibration method, and just check your posterior afterwards. Right. And the most important caveat here is that simulation-based inference is by no means plug and play. When you want to use this in your daily research, it will not work out of the box. It requires a lot of careful consideration and design choices that are meant to work with your particular area of expertise, the particular problem you have in mind. And you should first check on examples and simulation examples that you know, that you can even compress with handcrafted statistics where you know what the answer should be in terms of parameter inference, in order to verify that what you are going to do now makes sense. So there are many failure modes that can occur from a poorly constructed setup and framework of simulation-based inference. Summary statistics play a big role, untrained networks play a role, the network architecture plays a role, strategies of sequential inference play a role and can bias the outcome, and yes, also the simulation budget that you need, or just the sheer number of training samples you need is an important point to have a look at. So in principle, using simulation-based inference doesn't free you from many things. So you save time in a sense that you do not have to restrict your likelihood or your physics, biology, chemistry, neuroscience that you want to do by the parameters your likelihood function that you can write down can handle. You can go crazy and be as realistic as possible, but the time invest rather goes into checking that what you're doing and inferring actually makes sense. And treat this as a black box. It is not, it shouldn't be, but just pretend it is and validate before publishing anything. Okay, then here I provide you a little overview of the different packages that are on the market that you can use to play with simulation-based inference if you want for your problem. Especially the package SBI is implementing all of the three variants and also sequential inference and all of that. So all the functionality is there. It's also well documented. Go there. Then there's the Swift package, which is in particular implementing neural ratio estimation and prior truncation for the sequential runs, which is a different way of doing it. They have a bit of a different architecture, so it's easier in some ways to SBI to use, others not. Then you have, for example, also Lampe, which is there for the amortized posterior estimation, and it's modular one, and PyDelphi, which is another implementation of these algorithms. If you want something practical at hand, again, to read in terms of a paper, I link here this particular summary, which is more or less recent. This is well, quickly evolving field. So when I say recent, well, it's already a few months old. Who knows? But this is a good reference if you want to have a read of the more technical details. Right, and then yeah, let me come to the summary, at least of these more technical parts. So today we had a look at sequential simulation-based inference, which is a way to focus on a particular target observation instead of doing it in one round and having an amortized posterior. This is a good strategy once you really want to know accurate and precise answer to the posterior for a particular observation, and you do it via either prior truncation, depending on posterior outputs per round of your sequential inference, or via proposal methods that use the posterior you infer in one round as a prior in the next one. Well, there the current gold standard is this SNPEC, which combines kind of the best of both worlds of these proposal-based methods. You should always use diagnostics in order to at least verify that you have calibrated posteriors that behave well in terms of predictive checks, looking that your posterior produces simulations that at least look a bit like the real data you're analyzing, then doing marginal calibration and expected empirical coverage checks in order to know whether your posterior is either overconfident, biased, or overly conservative. As I said, coverage is a necessary check, but it is not sufficient. And in particular, you can have the particular problem of model misspecification that causes some of these diagnostic failures. If there's model misspecification, you need some kind of domain knowledge to know how to improve it. There are ways to do it. But in the end, a safe way is also to state that there are limitations to what you're doing now and improve on this in future work. And use simulation-based inference whenever there is no tractable likelihood. You need amortization, or you want to avoid compressing your observation too much that might eradicate or erase information that might otherwise be useful to actually constrain your parameters of the model. While traditional methods are still the gold standard where you can use them because they give you a well-defined and well-defined answer to the problem. All right. So, other questions? This doesn't seem to be the case. Then I'd like to say that on these slides, there are also some references that you can have a look at, and these slides will be uploaded on the lecture GitHub so that you can have access to them. What I would like to do in the last half an hour is to have a look at least some notebooks that make this a bit more clear what I'm doing here. Let's see. Oops, where is my here? About what you implement and how this looks in practice. Well, when I say in practice, then I'm not doing anything fancy. I'm just looking at examples that you can quickly code and that give you some idea of how you at least set your numerics up. What I will be using for these different notebooks are some Python packages as a typical implementation, and in particular the SBI package, which implements all of these different ways of doing simulation-based inference. And as I said, it's well documented. You have tutorials there, so it's a good way to check out how to perform it. Okay, so on this notebook, I just wanted to get everyone acquainted with null posterior estimation and how you would do it. So what we did in the lecture is discussing Bayes' theorem, how the loss of null posterior estimation looks like, and how you use normalizing flows to do this type of density estimation with null spline flows, and how it provides you with amortized inference. So what we do here is to define a simulator and a prior for simulation-based inference. We train this neural posterior estimation density estimator with the SBI package. Then we sample from it, from the learned posterior, and visualize the results, and then understand what amortization means in practice on just some sampled observations. Okay. Also, these notebooks will be uploaded to the GitHub so you can access them quite easily after it. So, what is the model I wanted to showcase here for this particular problem? Well, let's start with a linear Gaussian model. The linear Gaussian model is very simple. You have a parameter that is called theta that lives in a three-dimensional space. And you draw this parameter theta uniformly between -2 and 2 per dimension. And then what you do is this marks the central point of a normal distribution, which we add to this parameter, or its central point. And this epsilon here is then drawn from this normal distribution with mean 0 and standard deviation 0.5. And this is a non-correlated covariance matrix, so it only has entries on the diagonal. So basically, it's really like a nice, normal, not distorted in any direction. Right. And what you would do is then in this framework, you would define this prior, make it a uniform box from which you draw, and you define your simulator like this, which is exactly the implementation of this formula above. And in the language or the framework of SBI, this is how you simulate samples from it. You call this function here process simulator, where you input your variable theta that you want to infer, and you give it the prior that you defined here as a uniform box, and how you want to have this returned. Okay, then you do the simulation and generate training data. Well, how many do we need? That depends on the case. Let's just simulate 5,000 samples from the simulator. So what happens is that here it will sample this parameter theta 5,000 times and add some Gaussian around this. And you see that this would produce this type of, well, distribution, given your particular position for the target observation. All right. So normal, because it's a normal distribution as you would expect. And then what we need to do next is to train the inference. So as I said, SBI is very much modular and easy to use. So you just call something that is called NPE, so null posterior estimation. You specify a prior and you specify the density estimator, which is here this null spline flow that we discussed before. And then it's in principle just plug and play. The methods are defined. You perform the training data inference or training via adding this to the inference module and then training the module with its train routine. You can specify certain hyperparameters of the training as usual. They're documented on the SBI website. What to use. This is just some very simple, some batch size that you use for this particular problem. And okay, let's say we do this, and then you get some output posterior. It says it's converged after 40 epochs. Okay, cool. The best validation performance, so on and so forth. Of course, you can be much more specific in an actual example that is interesting from your science perspective. And as I said, to also log and monitor validation loss, training loss, and so on and so forth. But for this example, that will be an overkill. And once you have a trained posterior, which is already the final output we want, we can now define an observed data point and sample from the posterior. So let's say our true theta, so our true position for this three-dimensional Gaussian was at this particular position in 3D space. We simulate from that one noisy observation. And then from this particular noisy observation we've drawn, we would like to know what is the most likely position given the posterior we've just learned. Okay, let's draw 10,000 samples of the posterior given this target observation. And let's plot this as exactly such a corner plot or pair plot. We see here a histogram of the different points we've drawn in the 3 dimensions and how they distribute in space. The red line is the true value for theta in this dimension. And you see that indeed it looks as if the posterior is correctly positioned around the mean that should be there as the true parameter with something like a Gaussian posterior. Okay, so this is exactly what you want to see for this particular case. Right, and then we discussed the amortization property. So what does this mean? Well, again, this is this key feature of all of the simulation-based inference approaches. If you evaluate the same posterior that we have trained for different target observations, you get an inference almost immediately by just resampling a certain number of posterior samples for each of these target observations. So if we loop all through all those three target observations, we obtain exactly this, a projected distribution in each of the dimensions, hopefully around the correct value. And here, this red line is just for one particular observation. It's the observation here, the second one that marks that. And yeah, right. That is basically the gist of what you do. Then you also have a few other examples here that you can play with in the exercises. Okay, so basically this notebook is also an introduction into the syntax of this SBI package that you might use. I go through this without explaining too much about the syntax because, well, if you want to use it in practice, you can just read the documentation yourself. Okay. Are there any questions about this first notebook? All right. Then let me switch to the second tutorial, which now compares neural posterior estimation, likelihood estimation, and ratio estimation, still being employing the SBI package. And here, for purposes, I've chosen this different simulation target, the two moons simulator. I think also Gabi has shown to you this two moons example already when she was discussing normalizing flows. So this is some example that can be used as something that, well, shows you where there are some modes where you need to check or watch out for when doing simulation-based inference. Okay, so the idea is basically, oh, sorry, to produce a crescent shape, and the crescent shape is best noted here, something like this. Um, and what you want is to determine what is the exact position of the center of this crescent shape. Okay. There is, however, a little catch in this. In the definition of this model is a particular complex feature that allows the model to actually be multimodal, so that you can produce the same shape with two different angles that are here the random variables of the process. And this gives some confusion to the network and the posterior that needs to be learned. So this bimodality of this model, given an observation with a mirror image, will play a role, and that's a reason why you want also to use something expressive as neural spline flows, because they are more likely to learn such a feature than these masked autoregressive flows, or a different technique like neural ratio estimation, where also multimodality can be learned rather, well, in a simple fashion. Okay, so it's not so important how the simulator works. It's just that what I tell you, that it can produce the same image for different parameter constellations, introducing some multimodality. Okay, and now if we use this fixed theta set, and theta here is just a set of two angles in one dimension and in the other dimension that describes this problem. You see that the semicircle that is produced by, let's say, choosing 0.3 and 0.2 is also mirrored by minus 0.2 and minus 0.3. So both of these parameters would produce the same example. And what you want is that your posterior catches this. All right. So what you do, well, basically you set up the simulator as there, and the syntax remains the same. You produce simulations, here 30,000s, just for better resolution. And then we train our three methods in order to compare whether or not all three of them are capable of catching this bimodality feature. So what we use are neural spline flows for neural posterior estimation and neural likelihood estimation and neural ratio estimation. Okay, can be trained, and if you look here, so you see that there's already one difference since neural posterior and neural likelihood estimation use a different network architecture, and typically infer a joint posterior, they tend to take a bit longer during training. While neural ratio estimation here takes only about half the time because the network is simpler. It's just a classification network, so it can be a feed-forward network. And overall, it doesn't have to infer the full joint posterior. Although here it doesn't matter because they're just two parameters. Okay, and what we want to know is what happens now if we show to this samples sampled from the posterior for the three different cases of training. Okay, so let's have a look. With 10,000 samples and we bin the obtained samples for these two angles, theta1 and theta2, we see that, okay, there seems to be a multimodality. So the neural posterior estimation approach has produced this, and you also see that the two observations that would produce the same image are inside the posterior density. What you also see is that you have these points here that seem to connect these two. This is also something that you've seen, if you remember, in the example that Gabi gave about normalizing flows, that you have this connected part between a multimodal posterior, simply because of the fact that you started from a standard normal distribution, which is unimodal. So there's only one mode for it, but you require it to be multimodal in the end. These spline flows are expressive enough to get a split, but then you have still some kind of probability left that connects these two, because you can't really split this in this framework because, well, these are all differentiable smooth transformations. The same feature more likely can also happen in neural likelihood estimation. In this example, we are lucky it didn't happen. But you also see that the sampling of this likelihood takes much longer because you actually need to sample a likelihood in order to find the posterior points, while this one here was basically instantly done. So the difference in time is quite huge, like 3 orders of magnitude. While it's not that bad for neural ratio estimation, there's only a 2 orders of magnitude difference, let's say, between the time it takes to sample it. You also see that there is a true multimodality, but you also see that the training result is not as good as with the other two, which might be an indication that you either need more training data here, or that is simply the limitation of this particular method for that problem. Right. And exactly. As I said, you clearly see that looking at the timing, neural ratio estimation is the fastest in terms of training the network itself because of all the intricacies that come with it and where it can make shortcuts in terms of architecture and learning posteriors. But then sampling is fastest for neural posterior estimation because it is the fundamental property that you are sampling, while the others need other methods first in order to actually get the samples from what they derived. And again, there are some exercises in this notebook. Right, I think it's also okay. Let's go to the diagnostics notebook. First, we have questions regarding this comparison between the three flavors? All right. Yes. So then in the interest of time, let's go to the diagnostics notebook and see what you can do there and how this looks in practice. So here I go back to the old simulator that was simply being, okay, it's this Gaussian model with theta as the parameter. So this time it's only two-dimensional. You somewhere have the center of a Gaussian sitting, and you draw from a standard normal and you stretch it a bit along these lines, and so that you have a bit of a normal with a standard deviation of 0.3. All right, if you do this, we have our simulator, and we can have a look at what the predictive checks for the posteriors would look like. Okay, fine. Now, we train it with the typical method. We draw some samples and just have a look at them. How would they look? Okay, if I take this as my actual position, x0 of the Gaussian position, so how does it compare? Does it look reasonable? Does it look like a Gaussian as something that it should approximate? It looks fair enough. So at least from just looking at posterior samples, I don't see something that would tell me this is completely off. It's centered around the actual true value for the position, and it has a posterior that looks like a Gaussian, modulo the number of draws we have, so fine. Okay, then let's have a look at this first check for calibration. So the simulation-based calibration SBC test, where we select particular parameters and build this metric that just counts for a certain number of observed target observations and drawn posterior samples, how many times it is below the actual true value for that observation. So this can be done automatically in the SBI package. So they have this run SBC diagnostics tool. So this is already existent that you can just run, and it shows you the result basically of this. And what you see is basically what we want, a uniform distribution, so nothing is overproportionate. Of course, you have some wiggling around the optimal line, but this is expected. What is important is kind of the average you get over all of these bins. And this looks for both parameters kind of like 50-50. So yeah, fine. So like 50% are above, 50% are below this optimal line. So it just averages out. It's a uniform distribution, so we are happy. So this looks like a well-trained model. Now let's do something different and let's actually train something that will not result in something that is well behaved. For this, well, let's just simulate 50 of these Gaussian samples and use this as the basis for our training. Okay, and we use some very bad neural normalizing flow that doesn't behave very well, and with that number of samples, you probably won't get anything reasonable. Now, if we do this game again, yeah, you see that actually there is some miscalibration, and it goes directly into the line of being overconfident. So you see here there is a mismatch for the first parameter at the high end, and here it's kind of U-shaped. Both ends have this problem. So this posterior is probably overconfident. Why is it overconfident? Well, we just trained the thing on 50 simulations. And if you train a neural network on 50 simulations, what it is likely going to do, it will just learn these 50 samples and overfit them. So it will be very biased by having seen only these 50. It predicts very well everything about these 50 simulations, but not for a general point in your space, and that's why you get something that is overconfident. And this you can see here in this particular reconstruction. Okay. Like this. Still have 5 minutes, so yeah. Just to mention it, this notebook about sequential inference, which is also just showcasing the different syntax you need in this SBI package to do so, which goes again back to this very simple simulator of having a Gaussian, this time again 3-dimensional, with a certain center and a certain width, and you just simulate this, and you want to infer what is the center of my Gaussian. And what you do here is, okay, I start with a prior of my cube that is just very wide. So instead of -2 to 2, I now do -10 to 10, which is quite wide given the width of my Gaussian, which is only 0.5. So, well, there's a lot of empty space the whole thing needs to learn. How does it perform? Well, let's do it first in a single round, the training with 2000 simulations, and then also do a multi-round SNPEC algorithm with the same number of simulations, but in 3 rounds, and what the outcome might be. Okay, we can compare this, and you see here for the single round, this is the result, and for the sequential run, well, you basically don't really see a difference. So it works. What you don't see in this very simple example is how the sequential run would actually be more accurate than the single run, because for this very simple example, it's very hard to design something that is not easy to infer. That's why you see it like this. Right, what you could try to do is to focus the proposal distribution and just see how this goes round by round. But as you see here, so if you look into what it does in the different rounds, it is widest in terms of posterior, let's say in the first dimension of the theta parameter, and then it shrinks. But as you see here, it's not such a hard problem in the first place. So it's not as spectacular as it could be for a more complex example. And right, then there's some more exercises you can do with this, but in principle, that's how it works, also in terms of syntax. Unfortunately, there wasn't enough time to do this more physics example with throwing a ball, but this will also be uploaded so you can have a look at this in the GitHub if you're interested. But for that, I think this is enough for the lecture. And if you have questions, please, I'm happy to answer them. All right. Well, if that's not the case, then I think we can close this session, adjourn for today, and you will have, I think, an in-person lecture next time. And I thank you for your attention and listening to what I had to say about simulation-based inference, and maybe it will be useful for some of you in future research. So yeah, thanks. Have a nice day and a nice weekend, and see you around.
Thank you. Bye.
Bye.
Bye.